Andrew is the founder and managing director of Electromagnetic Imaging Technology and Absolute Geophysics based in Perth. Developed the Smart TEM electrical receiver system, Maxwell EM software that we've heard about and seen quite a bit of, the DigiAtlantis, which we'll hear about right now. And his specialty is in EM and particularly high conductance targets. And I don't know where he graduated from. I think he graduated from someplace, didn't you?
I never went to university, Dennis.
Oh, that's right. He never went. Yeah. Okay.
Just like you. Good morning. It's an absolute pleasure to be here, and thanks very much to you guys, especially for putting this on. I think people are going to be talking about this for a long time. It's a tremendous symposium. Well done. I'm going to be talking today about Borehole EM that was done, some surveys in Borehole EM that were done at Lalor in 2010. And this was done with a Fluxgate system. It seems like everyone's putting Fluxgates in boreholes now. We started doing it in 2004, and the system that we used was kind of unique at the time, I think, to put a low noise Fluxgate in a borehole and do EM with it. So this is a summary of what I'm going to be talking about. Just a bit of an introduction to that borehole system, a description of the surveys, some data including the EM data and the mag data from that magnetometer, some simple modelling, and some conclusions about the electrical properties of Lalor. This was the motley crew that did the survey. I think Matt Holden took this photograph, so he was here as well. There's Alan, the guys from Discovery, including Brent Robertson there, and some of the guys from Hud Bay. Brief description of this particular system. It's a triaxial Fluxgate Mag. I suspect that those of us that work with Fluxgate Mags in boreholes are probably all using a fairly similar sensor. As I mentioned, in 2004, we put a system together, and really it was designed to do a better job in borehole EM in high conductance areas, and we live and work around the nickel exploration areas in Western Australia, and that was the immediate target for this technology. In 2008, we upgraded it to turn it from what was really an analogue system with digitisation at the surface to a tool that was digital in the hole. So all three channels all three components of the Fluxgate were digitised in the tool and transmitted to the surface in real time. The original analogue system was one component at a time, really because it was an analogue system. Normally, these surveys are run at half duty cycle, and as I mentioned, converted to digital in the tool in the hole. There's a 24-bit A to D in the DigiAtlantis sensor, in the DigiAtlantis tool, and normally we're recording full on and off time series at the surface. It tends to work with most transmitter systems, courtesy of GPS synchronisation of our receivers and transmitter controllers. So those transmitter control systems are used to operate a range of transmitter systems, including the ones that we used in this survey. So as I mentioned, there's a simultaneous measurement and recording of the three components, and the three components come to the surface in digital form in real time. So the operator can have a look at raw data coming into to the receiver while the survey is underway. We do put a bit of effort into calibrating the sensitivity and orientation of the 3-axis mags, and also the 3-axis accelerometers that are in the tool. The accelerometers are used for deriving the roll of the tool and also the inclination of the hole. And because the Fluxgate Mag is a DC coupled sensor, we can use it to measure the DC mag as well. and really as a result you get the whole geometry out as well. There's been a little bit of discussion today about why or why not to use a Fluxgate Mag, and we've seen a bit of this already today. I'd add that due to the linear behaviour of these things, and they're pretty linear, they're easy to calibrate, and being a small sensor with relatively low power consumption, it's a no-brainer to put these things in a borehole. And at low frequency, and really the emphasis here is low frequency, at low frequency these things are a reasonable EM sensor. In the following I'm going to present data in the same form as previous talks with A, U and V in the kind of standard presentation, with A being the axial component. This is an example of the type of presentation that the operator gets presented with, and we use the same software for collecting the data in the field as we do for processing or any other kind of value add things in the office later on. And in this particular example, there's stacked time series here on the left, the three components. This is a plan view showing the loop which has been imported into this project, and the trajectory of the hole, and that trajectory information is coming out of the tool itself because it has the accelerometers and the mags in it, which really are just a digital compass. And on the right here is two presentations of the profiles, one with log scale and one with linear scale here. The particular holes that I did at Lalor in 2010 were the two holes here, and we've seen some discussion about both of these holes already this morning and I think yesterday. Dub 178 is the hole I'm going to focus on. Dub 33, I think there was some discussion earlier this morning about that in Sid's talk. Dub 178 sits above and to the southwest of Lalor. There, it's roughly 200 metres from the leading or the top edge of the deposit. I won't show you much data from Dub 33, but it's some distance away to the west, and it's really in a more complex part of the body. The surveys here used what's referred to as Loop 5. It's a historic loop that was originally designed to couple with the deeper parts of the Lalor deposit. Courtesy of Discovery International, we had a Phoenix 30 kilowatt transmitter generating 18 amps on the survey. That's quite a large loop. And as I said before, we run these surveys at half duty cycle. This particular survey was run at 1 Hertz, which is a fairly standard frequency for EM with Fluxgates today, and there was some data collected at a lower frequency, 0.5 Hertz. So that gave us, does that give us roughly half a second of off time to play with there. The readings done in the surveys were roughly 2 minutes duration, and there were several repeats and infills done. But the point being, in 2 minutes you've collected 256 stacks on 3 components, and they're all coming in at the same time. This is the data from Dub 178, and you saw Fluxgate data from this hole in the last talk from Josh as well. There's the section here. So this hole sits above the deposit. This is a typical log scale presentation. There was a few points. I think there's only 5 points across here done at 0.5 Hertz, so going to 500 milliseconds of delay, but the rest of it was done at 1 Hertz. And this is these channels in here are all sitting well below 1 picotesla per amp. So axial, and these are the 2 transverse channels here. I've just highlighted the 0.5 Hertz readings there across the main crossover in the U component, or the peak of the off hole in the axial component. Same thing with a linear plot. And looking now at the late time, so beyond 40 milliseconds, this is just a linear plot of the data beyond 40 milliseconds. You can see those later channels sitting right there at the bottom. Oh, and this is probably the only plot I'm going to show of the data collected in Dub 33. It's a slightly deeper hole. Further away, there's clearly a nice off hole in the axial. Whether the long wavelength feature is in the cross holes is up for debate. Anyway, that's probably the last slide I'll show of that particular data set. I'm going to focus on Dub 178. Just another example of another deliverable from the survey. We calculated the on time. Because we're recording the on time and the off time, it's pretty easy to put windows in the on time. And this is an example. This is the calculation of the theoretical primary versus the measured late on time field. And if you take the difference, I think I've got a problem, an error in my annotation here. This is really the late on time minus the theoretical primary. You can look at the equivalent of a step response or an on-time B-field measurement. So in the late on-time, there's really no detectable feature here in the late on-time. But no feature that we can resolve there in the late on-time. The magnetics, it's really just a byproduct of measuring EM with a DC coupled magnetometer. The three components here. So we're looking at components in the borehole reference frame here. That's why there's a big variation in the response at the top, because the hole is shallowing as it gets deeper. I guess if you displayed these in east, north, and vertical components, you'd see these being pretty flat. You see a fair amount of magnetic fabric in the upper part of the hole, less so at the bottom. And this is the total field mag, which is really just a vector sum of the calibrated outputs of the three components. So that's just one more deliverable there. And this is kind of beyond the scope of this talk, but I threw a quick model in here to have a look at the conductance that would lead to that anomaly in Dub 178. And this is the kind of model I came up with. This is far from being an official model from the group at Hud Bay. It's just something I just used to simulate the response. And this particular plate is almost a kilometre by a kilometre and has a 600 Siemens conductance. As I mentioned, it's a couple hundred metres from that borehole. I'm only really trying to fit the data beyond about 40 milliseconds, so the late time three-component data here, and the fit is really quite good from that plate. That plate sits right in the same horizon as the TEM lens, which is the zinc-rich, massive upper portion of the Lalor deposit. And if you move that to any other place, the fit is far from perfect. So the late time data from that hole really does image the TEM lens very well. So in red there is the model response, and in black is the field data. Just to emphasise the excuse me, the fit of the axial component data. That's just a blow up of the A component there, with the model response in red, and that's just the data beyond 50 milliseconds, including the data out to 500 milliseconds there at the bottom. Just briefly, some decays from one station in this survey. So this is at 500 metres, so reasonably close to the centre of the anomaly. We just look at these decays. There's the 1 Hertz decays finishing here at about 250. They're on the axial component here. The 0.5 Hertz decays sit above that in amplitude, and that's because the lower frequency is energising the longer time constant parts of the response, just simply by virtue of being at a lower frequency. And that's exactly what you expect to see when you model a reasonably conductive target. So there's a couple of repeats here in all these components. So you can see the repeatability, this being 1 picotesla per amp here on this linear section. And just to repeat what I said, that's the lower frequency data sitting on top there. So I'm just going to have a look at the time constants from those decays. If you calculate a time constant on the late 1 Hertz data, the late time 1 Hertz data, you get roughly 80 milliseconds. And that's a number that's pretty high when you think about the taus that are reported for VMSs from, well, for example, a 30 Hertz ground survey or an airborne survey. So we're talking about pretty long time constants here. If you look at the 0.5 Hertz decays from the same station, the time constant is more like 110 milliseconds. And the decays haven't quite got to their final exponential decay at that point. So you'd argue that, you might be able to argue that these conductors are somewhat unbounded down dip because they're not really getting to a nice exponential decay anytime quickly. So just wrapping up here, the sheer size of that deposit dictates that you do have a significant EM response, and the conductance. If we take that model as an example, the conductance of the 10 lens is something between 500 and 1,000 Siemens, but and I think that's probably a typical sort of VMS type conductance. But the sheer size of it means that the decay constants from that data set are in excess of 100 milliseconds. If you look at the signal to noise in that hole, you could say that you could easily detect Lalor from several hundred metres away in the hole, and that particular hole was around 200 metres away. You could easily double the distance and still detect it from that particular loop, and probably more. And just a comment about the modelling, simple EM models do a pretty good job at simulating Lalor, especially in that hole which is off to the south there, even though it is quite a complex stack of pretty thick conductors. And as I mentioned before, you might infer from the kind of decay behaviour there that the whole system is pretty big and in some sense it's kind of unbounded. And in my opinion, measuring off time B at low frequency is a pretty powerful tool for doing geophysics on VMS targets. And I think one of the important take-homes is that doing that lets you discriminate the more conductive parts from the lesser conductive parts of these type of targets. And I don't think that doing low frequency EM really means that you need to have a very long measurement, and long measurements are really the enemy of the accountant when it comes to having drill rigs on standby. I think we all know that. I'd really like to thank the guys at Hud Bay in Flin Flon and Snow Lake and Toronto, the guys at Discovery and the guys at and Dave Coop's business who all provided logistical support and ongoing moral support. Thank you very much.
Open to the floor for questions. Well, look, I've got one, and I hate to put everybody on the spot here, but this is directed to Alan and Dave and Josh and you. Do you or do you not see the Lalor deposit in hole 33 at 600 meters away? In 33, are you or are you not seeing the Lalor deposit at 600 meters away?
Yeah, Matt's there.
Here earlier. Okay, I think I have to answer it this way. In fact, I had a question for Andrew. We've all seen plots from several surveys, from the original Crone survey, recent Crone surveys, the Crone Mag sense of your DigiAtlantis, broad anomaly. I've tried to model it a few times, and others have tried to model it. I don't know if you actually got a distance on it, Andrew, but to answer the question, we now are confident, and I'm talking about what the work that Matt did and that I did previously. The question came up, you asked it earlier, can we get a direction on that distant anomaly? And I said, yes, I believe we can, and it's pointing towards Lalor, but the distance, everybody's seen all the plan views, the Dub 33, the actual intersection in Dub 33 wedge 1 is approximately 600 meters away from the known lenses. So it's not seeing the ore grade material, the near edge, it's seeing the near edge of the highly conductive material in the neighborhood of 400 meters away. But I don't, did you ever model it, Andrew? Like, do you have a distance?
That model works pretty well for the axial component long wavelength anomaly in Dub 33.
Yeah.
That model right there. I don't know what the distance is.
I had always put it at somewhere around 400 meters, greater than 350, but because it's
Yeah.
not a complete curve,
Yeah.
it's not a perfect model
Yeah.
of the 178.
Yeah.
I'm not sure. I'm just asking if you, and in fact you said you figured we could easily see double the 200 meters distant away.
Yeah.
And
It's so much simpler on the south side down here to kind of pick distances and but on the Dub 33 side there's clearly a lot going on local to the hole, which is not part of your normal, which is not part of your economic your assemblage there. But I don't think there's any doubt that you can see this thing from Dub 33 on the axial component in Dub 33.
Are you saying the cross-hole components match this model from Dub 33?
No.
They don't.
No, I think they're more affected by the local stuff. But Matt had an opinion on that.
yeah, let's hear your opinion on that, Matt, because you were the one that originally said you thought you could get a direction on the X at least, but not on the Y. Is that not correct? So the Y was better than the X. Maybe I didn't remember it correctly, yeah.
Yeah, good point. Excellent point. And, at 500 meters, I mean, correct me if I'm wrong, but that sounds like about the farthest I've ever heard of detecting a conductor away from a borehole. Anybody heard of anything better than that?
Well, it's the perfect storm. It's a huge thing. It's a huge conductor. And if you can detect it from the surface at a kilometre, right? There's no reason why you wouldn't detect this thing at 500 metres in a borehole. Yeah.
Any other questions? Okay.
That's what I love about geophysics. You can get 4 different people with 4 different opinions, and you still think, man, those guys are all really, really smart.